So because of time, so if you look at base rule, right? So base rule. So this probability of G is equal to K, right? Yeah. So that's a number. Okay, between 0 to 1. Instead of that, I will just use pi q. Oh, all right. Okay. And in this thing, we are determining different number of deltas. So so these delta functions are linear. Yeah. And there's only one function per class. So that's why that is the class master. Yeah. So you have, we have the same number of functions even for linear regression, except in linear regression the way overlapping functions. Yeah. Because there's no, I guess in linear regression you still have k functions, except those k functions will not give you the right decision boundary. In this case you have k linear functions, but they are kind of specific to each class. I guess even in linear regression they are specific to each class. So I guess the answer is a little more complicated than that. Alright, okay. So I can explain if needed. Let me think about it. Sure. Okay. So now I just I can assume that this delta are simpler linear lines. Yeah. That avoid class mass. Yes. Got it.
How do you choose like a project topic, or is there?
How do you choose a project topic? Have you worked with any data set before, or have you worked in any industry before?
No, I discovered.
Then I think I provided a link to data.world, right? That seems to have some data sets. Try to mimic the assignment type of analysis, like the kind of analysis that you do in assignments with KNN or linear regression. You can mimic that on any data set of your choice. If you can mimic that and try to do it in a more careful way, because if it's a new data set, then there is not going to be any established ways of doing it, or somebody else may not have already done it. So that would be that could be a contribution.
I think I'll go through it and cover this.
Okay.
So in linear regression, suppose we have one-dimensional data. So what we are actually doing is, correct me if I'm wrong, we are segregating the x values with one particular label. We are building a regression function out of it. We are drawing it, and then we are selecting at each given k what is the maximum of each predictor.
Is given x for a given. So you just find for a given x you have k numbers. Linear regression will give you k numbers. Okay, think of it this way. For any fixed point x, it's as if you have done k one-dimensional linear regressions. Okay.
K one-dimensional linear.
One-dimensional just means that the output is one-dimensional.
Yeah, understood.
Okay. You have got k predictions. Just take the max of them.
Take the max of them.
That's okay. That's what linear regression.
In linear regression, we are building the number of equations which are equal to number of classes.
Yes.
Okay. And when we input the test result for predicting, we will get outputs, number of outputs which are equal to number of classes.
Yeah.
And within these outputs, we will select the maximum one.
Yeah, as your class prediction.
Okay. And in linear discriminant analysis, we
still do the same. We have k functions.
We are still building k number of equations.
This discriminant functions is for each subscript to the class. So for each k you create this linear function. It looks like a very messy function, but it's just x transpose something, okay, plus some constants. And these constants are just functions of data.
So how different is that? Because of this function, it somehow gives the better kind of equation, better kind of segregation.
Because this directly focuses on the decision boundary. So we are directly comparing
mean and covariance. It focuses on that.
No, we are directly comparing these conditional distribution of G is equal to L less than the conditional distribution of G is equal to K. Okay. This is actually the same comparison that you do in linear regression. But the trick here is that we assume the exponential form here for f of k. Exponential in the sense because we assume f of k of x to be normal. There is an e to the power something here. Where is it? Yeah.
Okay.
If you just compare these two numbers, there's an e to the power x minus mu transpose sigma inverse. So if you think of linear regression, in linear regression this is a linear function of x.
It is kind of a transformation of x, and that gives us better decision boundaries.
Yes.
Okay.
So here you are supposed to actually compare e to the power minus 1/2 this compares to this, but you just said I took a log because both sides are e to the power something, and it just happens to be, if you take the log, it just happens to be linear.
Okay.
So there is a log transformation which is getting you to avoid class masking.
So log transformation is avoiding class masking, or just exponential transformation is avoiding the
Log and exponent are just same thing. I mean, when I say log transformation, the exponential assumption about the f of f's. Yeah.
Okay, understood. Okay, and my second question is regarding exams.
Yeah.
So in exams, is it going to be kind of derivation or
There are sample exam questions in every lecture. You should look at it. Every lecture notes.
okay, so I will look into that. Yeah.
So have a look at it. If they look like derivations, then you'll have derivations. If they don't look like derivations, then you may not have derivations. Yeah.
Okay, and for project, I got one data set from Kaggle. It is regarding trip duration for New York taxi.
Okay.
It was a previous competition as well. So, but then it is kind of a prediction. So most of the times I won't be able to use regression models.
Why?
Classification models.
That's fine. So why do you care about using every technique? Just use something.
Okay.
It's all problem dependent. You don't have to use all techniques. Yeah.
Okay. Thank you. Yeah.
Also, in that function, can you describe what does it mean? What's there in the denominator exactly?
If you see the expression for p of g is equal to k given x is equal to x, I just defined it here, right? That is fk of x times pi k divided by this denominator. Okay. Whether you change the numerator to k or l, you'll have the same k or k prime or some other class. The denominator will be still the same. It's a sum over k such terms.
Okay, that's why it's getting cancelled.
Yeah.
And can you scroll?
Up. Okay.
I'm not sure. I think I missed out on a lot of your sentence, but while discussing about class masking, you have stated saying that for any new x naught, no new prediction is made. I don't really understand what that is.
No, predictions are always made. It's just that you will never predict y2. In this data set, it happens that for any given x naught, either the first quantity will always be max or the third quantity will always be max. So y2 is never predicted. That's all I said.
Oh, for any new x naught, as in some random x naught,
Yeah.
y2 can only be predicted as maximum. That is
Yeah, we'll never predict it as maximum. So you'll never predict, even though there are three classes, you'll only predict like the first class or the third class all the time, which means that you're missing 1/3 of the data. I mean, in the sense, 1/3 of the time you'll be incorrect because in our true model there are three classes.
And that
I mean, ground truth there are three classes. Yeah.
and that second class can be any of the three classes that is given, right? Random.
No, I mean the second class is the blue. I mean, I don't know what color it is, but
So is it fixed?
no. So I'm fixing it. So this is just an example. This is a particular data. This is how the two input variables look like. I mean, every realization, and this is how the classes look like: the blue, orange, and green. For this data set, you will not make a prediction. The second class will make. The second class is not predicted.
Okay.
But for other data sets, you may get. You will probably have. If you use linear regression, you may get a prediction y2. I mean, class being
So in
second
general,
class.
we will be predicting only the extreme classes, not the one which
No, that's not always. In this you will be only predicting extreme classes. In this example, but it's not always the case. So you can use linear regression for classification in general, but there may be a pitfall of this.
I just want to make it, sorry, I just want to make it clear So if you say there are three classes, yellow, blue and green, and for that linear regression, blue is my second class and blue was in the maximum value.
Yeah.
Suppose for the same three classes, there's another linear regression, probably that is, I don't know.
No, it will not give. What is something else, right? Linear regression will only give you this answer. I mean, we are seeing decision boundary here, but linear regression will give you 3 lines basically, like these
I'm
blues.
saying that blue is always going to be my second.
It's always going to be worse, yeah. So actually 2-dimensional plot is probably not useful. Actually, you can just think of the data being 1-dimensional like this, where there's here, if you look at orange, blue and green, these are the 3 buckets. So in each side you want to predict, like here you are supposed to predict orange is the highest, here you are supposed to predict blue is the highest, but it just happens that because of linear assumption, blue is never going to be highest yeah, in this data set. And so here green is highest as expected, but the moment you introduce interaction terms, second order curves, then blue happens to be highest in this region, so you're fine. Yeah. So 2D is probably a bad representation. Yeah, mean of each case. So for each, okay, this is not useful. Yeah, I said for. Yeah, so for fk, there is a mu k. It's a mean of the multivariate cross. Okay, so let's assume. So actually, somebody asked me during the break, how does this differ from linear regression? How is it actually countering class masking? Okay, and I probably didn't explain it correctly. So I guess I didn't point it out. But if you remember, in the linear regression version of classification, we are assuming that the conditional distribution of yk is equal to 1. So probability of yk is equal to 1 given x is equal to something. We are assuming it to be a linear function of the feature, right? We are actually assuming that the conditional distribution of y given x is actually linear. Okay, and since yk is an indicator random variable, you can this thing is the same as probability of g is equal to k, for example. Okay, I mean, yeah. So we are saying that the probability of g is equal to k is just a linear function of x. Okay. In linear discriminant analysis, since we introduce this conditional distribution to be normal, we are saying that the probability of g is equal to k given x is equal to x is some very complicated nonlinear function of x. Okay. You can see that, right? This fk is e to the power minus x times something divided by, in the denominator there are so many Gaussian terms. So this is actually a very nonlinear function of k. The conditional distribution of g is equal to k given x is equal to x. Okay. But even though this is nonlinear, it happens that the decision boundary is just linear, because I just said if you compare two classes L and k, and if you like at the decision boundary this is actually equal, right? If you just compare two conditional distributions, take the log and everything, you will see that it is actually just a linear comparison. Okay, it's going to give you a line basically in 2 dimensions. So that's the big distinction between linear regression and linear discriminant analysis. The conditional distribution is directly assumed to be linear in linear regression. The conditional distribution of g is equal to k or yk is equal to 1 given x is assumed to be some some nonlinear form, that fk of x divided by some complicated sum, right? So that's the distinction. But for both of them, the decision boundaries are linear. That's all. Okay. And somebody also asked, what is this pi k here? So why did you have to have an additional? What is pi k? Pi k here is a scalar. Okay. It's just a number. Is a parameter of this model. Okay. There's going to be one per class, and they're going to kind of capture this marginal distribution of the class itself. So probability of g is equal to k. Okay, is going to be captured by pi k. Okay. So that, you don't need to know the Bayesian interpretation. Just that if you look at this assumption about that the LDA makes, then there's fk which has mu k as a parameter. It has sigma as a parameter. So those are 2 parameters now. There is pi k as a parameter, and you have nu k and pi k for every k is equal to 1 to k. So there are those many parameters. There are a lot of parameters compared to linear regression actually. Let me account the parameters again. So for LDA, are going to be pi L. L is equal to 1 to k. There's going to be nu L. L is equal to 1 to k, and there's going to be sigma. Okay. So this is k numbers. There's going to be k times p, or k times p numbers, and this is going to be p times p numbers. I guess covariance is going to be symmetric, so I guess let me just say order p square numbers. Okay. So these are the total number of parameters in this model. If you compare linear regression, you just had k times p numbers, which kind of parameterize beta hat, right? Beta hat is k times p dimensional, or p times k dimensional, one of those. So the number of parameters is increased in this model. Okay. And I said using training data you can compute these parameters, right? The discriminant function is written in terms of the unknown parameters sigma, mu L, and pi L, but you can compute these parameters, and it turns out, they're not going to explicitly derive how these parameters are computed using training data, but it turns out you can just use maximum likelihood. Method. If you remember maximum likelihood method, all it's saying is I have some data z1 to let's say zn, and I want to estimate a parameter theta. Then you just write the likelihood of the data. This is our data as a function of at any given theta. So likelihood theta, and this is you maximize over theta to get a theta hat estimate. Okay. So we know the likelihood of data actually here, because we assumed the functional form we assumed f(L) of x. So we assume that x, if it is in class L, is exactly normally distributed. So we assume that. So in the data, if you see for class L there will be a bunch of points, then all you need to fit, this is parameterized by mu L and sigma. So if you need to fit the mean of the Gaussian, you just take the average of all the points in the class L in your training data set. Okay. There's really nothing complicated going on, so I'm going to skip how you estimate the parameters of LDA. Okay, but it's just maximum likelihood. Okay. It's just count and normalize type of thing. You just count or take averages of things from your training data. So there is no optimization here. The parameters for linear regression, you actually have to do matrix inverse and stuff. I guess for covariance estimation here, covariance estimation of your data, you will probably have to do inverse or take the empirical covariance matrix. For means, it's just an average, and pi's are also just average. So there is no complicated computation going on here. In linear regression also there is not much of a complicated computation going on. There is still a matrix inverse x transpose x inverse that may become tough if you have really large dimensional data. Okay, so then P is, let's say, a million cross million. A million cross million inverse may not be a good idea. So those are things which you may want to take into account if you are looking at really large dimensional classification regression problems. Okay. So that's about LDA. So I'll just give an example of, I guess I'll just leave a question here, which is, what if one of my xj is categorical? Okay. Can I use LDA? What do you guys think? So let's understand this question. When I say xj is categorical, I'm just saying that the jth coordinate of my input variable is categorical. It just means that there is no ordinal relationship between, there is no relationship between the values that xj takes. So let's say xj takes a value summer and xj takes a value winter. There is no relation between summer and winter. Like, what are the numerical values that you can assign to them, right? So that's what I mean by categorical variable. So if xj is categorical, can you use LDA? What do you think? So who thinks we can use LDA? It doesn't matter whether it's categorical or not. And there's only one person. Okay, who thinks we cannot use LDA when things are categorical? Any rationale, or is it just flipping a coin?
Well, that's definitely like a Gaussian continuous distribution for the class, right?
Yes. So the answer is we assume that the distribution of x is Gaussian, multidimensional Gaussian, and if x is categorical, that's a very bad modeling assumption to make. Okay, so that's what he pointed out. Is that clear?
Can't we change the categorical into numerical and give random numbers without hardware?
Yeah, if you remember, there's one trick that we proposed in the class, which was if there's a categorical coordinate, then you will create additional, xj1 to xj m. So let's say it's a categorical variable which takes m values. Okay, summer, winter, autumn, and maybe fall. So whatever, 4 values. Then you can create these dummy variables. Okay, then you kind of have resolved issue of categorical variables to dummy variables. But then still these variables are not Gaussian, right? Because we are assuming the whole x is Gaussian given class L. I mean, for every given class L, it's a Gaussian with different mean. That's what the FL assumption means. Okay, with different means. So we can't do that. I mean, you can do it, but it's probably a really bad assumption. I don't know what performance you'll get. Okay, so next let's look at a very closely related technique called logistic regression. Okay, it's going to be an improvement over LDA. So how many of you have seen logistic regression before? Okay, so I can skip the. So do you know? Okay, actually, let me compare logistic regression to LDA in a couple of minutes. So I'll just recap what logistic regression is for people who have never seen it before. It's not a difficult model at all. Again, it's going to make an assumption. Okay, everything starts with an assumption. So we don't have data, we don't have a joint distribution. Start with assumptions. So we're going to make an assumption, which is that the log of the probability. So in classification land, we always have to think about the conditional probability of the class. I mean, conditional probability of the qualitative variable taking a class, taking a the probability that the class takes a value, the random variable takes a value L, given x is equal to x. Okay, we always have to think of these conditional probabilities. And logistic regression makes the assumption that the log of the probability of G is equal to L divided by the probability of G is equal to, let's say, the last class, without loss of generality, as in you can pick any class in the denominator. Let me pick the last class, given x is equal to x. Okay, the log of this is equal to beta L transpose x. Okay, so this is the assumption. It's a weird assumption, right? I mean, I'm saying I have k classes in my classification problem. I'm saying I'm going to take the ratio of every class from 1 to k minus 1. I'm going to take the conditional probability of G taking that class value given x is equal to x, divided by the conditional probability that G takes the value of the last class given x is equal to x, take the log of that, and I'm going to assume that to be linear. Okay, saying the ratio of the conditional probabilities, the log of that is linear. That's the assumption. And now we'll say, okay, why make this assumption, right? It's actually partly motivated by looking at LDA. So in LDA, if you look at the, in LDA we made different assumptions. We said, okay, the conditional probability is going to be some f divided by some bunch of summations, and f is going to be normal and so on. But even if you make all those assumptions, if you just look at the log of the ratio of these two conditional distributions, even for LDA, it just turns out to be linear. Okay, you can verify that. Yeah, because if you remember, log of for LDA, log of P of G is equal to L given x is equal to x was basically the discriminant function delta L of x, which was linear, right? And you know that log of A divided by B is log of A minus log of B. So I'm just subtracting two linear functions, right? So if I take log of Pg equal to k given x is equal to x, that's some other linear function delta k of x, okay, which is also linear. So if I subtract these two logs, that is basically this ratio for the LDA case, and in the LDA case also it is linear. So without making the Gaussian assumption, I'm going to skip two steps ahead and say whatever be the class conditional density, so the f case, whatever they be, I don't care. LDA makes an assumption that FL of x is Gaussian. I will not make that assumption. I will directly jump two steps and say the log of the conditional probabilities of the classes is going to be linear. Okay, that's the starting point for LDA. And it turns out that if you make this assumption, then you can show that the probability of G is equal to L given x is equal to x is the form that you may recognize. It's e to the power beta L transpose x divided by 1 plus summation over k is equal to 1 to k e to the power beta k transpose x. Okay. And why is it called logistic regression? Actually, it's called logistic regression because this transformation is called a logic transformation. Log of the conditional probability ratios is called a logic transformation. That's why it's called a logistic regression. Okay, that's why there is a name logistic. Why it's called regression? Probably a misnomer, I would say, because it's a classification technique. So I said, okay, this is the assumption, and from this assumption I can actually show that the conditional probability of a class is just this ratio. Okay, again we got a ratio very similar to the ratio we saw in again we got a ratio similar to the ratio that we saw in the LDA assumption, right? In the LDA assumption there were some numerators and denominators, but there was FL of x times pi L or something like that, right, in the numerator. And I will just throw a hint of how you can, so just based on that assumption you can actually get this, and to get this you have to use the property that the sum of probability of G is equal to L given x is equal to x, sum over L is equal to 1 to k. What do you think this is? Put in a number there. Yes, that's 1. So if you use this property and the assumption, then you can actually see that the same betas, we assume beta L transpose x, right? So the same beta L transpose x, comes up. So just using the sum of the probabilities sum to 1. I mean the sum of the probabilities is equal to 1, and that assumption you can just see that this is true. Okay. And okay, so this is fine. This is just a modeling assumption. Okay. And it turns out because we are directly assuming that the log of these conditional distributions is linear, the decision boundary is again going to be linear. Okay. because remember the decision boundary was when the numerator is equal to the denominator. Then I'm not able to say which, like I'm at an x and both probabilities are the same, then I'm not able to say which class I'm going to be in, right? So when numerator and denominator is the same, then you see the log of 1 is 0. So the decision boundary is going to be beta L transpose x is equal to 0, which is a line or a hyperplane, whatever, in higher dimensions. But basically a linear decision boundary. Okay, so we still have a linear decision boundary, and so it's still a linear method. Okay. And the way, so with any new technique like linear regression or logistic regression or LDA, there's always going to be parameters that you want to estimate with data. So in the linear regression case, we had data xi, yi, which were n in number, and we got this beta hat, right? Somehow using x transpose x inverse, x transpose y or something like that. For LDA, I said we can estimate the pi hat L's, the means of the Gaussian distributions that we assume and the covariance. We can estimate using maximum likelihood method. I just said that 5 minutes ago. Okay. Now, how do you estimate the parameters of logistic regression? Okay, so the template is going to be for any new model that you propose, whether it's linear, LDA, logistic regression, or your own brand of classifier. You will have to specify the model. That's what we have been doing, and you have to suggest a way to estimate the parameters of your model. Okay, and that's what we did. For linear regression, we said there's a closed form expression. For LDA, we said we can use maximum likelihood. Even for logistic regression, we will have to use maximum likelihood. Okay, we will have to use maximum likelihood, except there is no closed form expression. For beta L's. Okay, so beta hat L's, so there is going to be L is equal to 1 to capital K minus 1, right? So these are the parameters. So how many, so this is going to be, each beta is p dimensional, so K minus 1 times p, this will be the number of parameters. Right? So there is no closed form expression for these parameters, these numbers that completely specify a logistic regression model, right? In a sense, given data xi, gi, right? I is equal to 1 to n. I want to get this beta hats, else L is equal to 1 to k minus 1. So somehow I need to transform data to these parameters, and that transformation you will do, I mean, this is a way of saying that you will do maximum likelihood to get these parameters. Okay. So I'll just write down what the likelihood function for maximum likelihood expression is, and it's not a black box for you. Actually, all we want to do is maximize the probability of G is equal to GI. Okay. Yeah. GI given X is equal to XI, and this depends on those betas, right? So let me call this whole bunch of betas beta 1, beta 2, beta k minus 1 to be a shorthand notation theta. Okay, I don't want to write this whole bunch of betas, so I'm gonna subscript this probability of G equal to Gi given X is equal to Xi for any given parameter, right? For any given bunch of beta L's, I can compute this number. I just want to maximize this number actually over theta, because this is what I observed. In my data, I observed for an Xi what its class was. Maybe for a given feature it was a cat, for a given feature it was a dog, feature vector, right? So I just want to set these parameters beta hats such that I actually make that prediction. I want to maximize the probability that I predict it to be cat or a dog, right? So this is called the likelihood function, And if you notice, I'm missing something, which is because I have n data points, I'll have to do I'm doing a product over I is equal to 1 to n. Okay. This is the joint likelihood of all the data. So the one term that I wrote was the likelihood of a single data pair xi gi. I want to write the whole likelihood for the whole data set. This is going to be a product, and then I'm going to maximize over theta. So this is what the likelihood maximum likelihood estimation problem would be, and it's just that this maximization problem doesn't have a closed form expression. By closed form, I just mean, remember in linear regression we had a objective which was squares, like RSS objective, and we still said we had a beta hat just directly in terms of x's, like x matrix, like we had a closed form expression. That's all I mean. So you don't have to compute something to get a numerical answer. You can directly have an analytical or a expression for what beta hat is in linear regression. Here you don't have. That's all. So any questions with what is logistic regression? It's quite straightforward extension or variation to LDA. So we made some assumption and we said this is how you estimate the parameters of this model. Okay. Okay, now let's actually come to the critical part. This may be very boring to some of you who have already seen logistic regression, but the differences, so relation to LDA is going to be the first one is going to be statistical relationship, and the second one is going to be computational. I guess not relations, but differences. So computational, we just said both need maximum likelihood estimation. Both LDA and logistic regression, estimating the parameters is going to be through maximum likelihood estimation. It's just that LDA has closed form expressions. So if you remember, there was a sigma, right? So sigma I had to estimate using sigma hat, and this you can very easily estimate as 1 by this n minus p, but sum over xi transpose. Okay, I is equal to 1 to n. So this is an estimator for covariance. Okay, this you can just look at the notes. Okay. And estimated for a mean for a class L is just going to be just do the summation 1 by, maybe there are L points in this class L, capital L points, then you just do a summation over xi. Summation over I is equal to 1 to L points. So the L points that belong to this class in the training data, just average them, you will get an estimate for the mean. So this is the estimations for LDA. On the logistic regression side, you have to estimate beta hat L's, right? Those you cannot have a closed form expression. And the statistical relationship or the statistical difference is that in LDA you're making an assumption about the conditional distribution of the features given the output variable, right? So we are making an assumption about FL of x, okay, which is actually just equal to, I don't know, write it, but it's a normally distributed assumption. So normal distribution assumption, right? So we don't make any such assumptions in LDA. So no such assumption. In logistic regression. Okay. So there is no class conditional distribution assumption in logistic regression. Okay, when I say class conditional, it's basically probability of x given g is equal to k. Class condition on the class, tell me what the distribution of x is. In LDA, it's normally distributed. Okay, it's just a. Yeah, again the same thing. Even for LDA, you write down the same thing. You can write this expression for LDA as well. But this expression for LDA has f divided by some summation over f's times pi's, right? But you will see that if you do that, you will get this closed form expressions for the parameters of the LDA, which are going to be sigma hat, mu hat, and there's one more parameter called pi hat L. Okay, so these three parameters you will get very simple solutions. Okay, like for two of them this is a solution, for the third one for example this is just the, if there are it's going to be just a number of so pi hat is just going to be out of my data set how many belong to number belonging to class L. Okay, so if my data set has 3 classes and my data set has 100 points and there is 20, 40 and 60, then pi hat L for the first class is going to be 20 by 100, second class is going to be 40 by 100, and third class is going to be again 40 by 100. Sorry, they have to sum to 100. No, when you have categorical input variables, then LDA may not be appropriate. But LDA is for classification. Yeah. Any questions? There is some joke over there? No? Okay, so that's it. Classification is kind of easy. Okay. I mean, at least in theory it's easy. In practice, a lot of companies spend a ton of money on getting good classifiers. Okay, so now we're going to shift gears and think about model selection and assessment. Okay, so this comes back to the cross-validation technique that we saw for subset selection. We're just going to rehash, recall what we did for cross-validation and just kind of put that in a firm grounding. So what exactly are we doing there? Okay. Okay, so actually let's, so what exactly do we mean by model selection and assessment? So assessment is somewhat of it's a related task, but all it's saying is I have a model, let me use F as a general representation for a model. So given any test point X, it either makes a prediction G hat or it makes a prediction Y hat, right? Let me just for any given X, I can make a prediction which is a regression quantitative variable or a qualitative variable. So assessment just means how will the model perform in the future. Okay. So you want to state that even before using the model in the future. And model selection is a related task where it's all about I have multiple models f1 of x to fm of x, and I want to say I want to somehow prune out all these n minus 1 models and say I want to pick f little m of x as my model of choice. Okay, that's model selection. It's quite straightforward, but what do we want to do? So we'll understand both model selection and model assessment through a topic that I introduced I guess 2 lectures ago, which is called the bias variance trade-off. Okay. Yeah, so think of these M. So I'll give an example of what this M means. Think of this M as the choice that you're making for subset selection, for example. If you remember, I had P dimensional input variables. I have 2 to the power P minus 1. So I have tons of subsets from which I can create one final linear regression model, right? I can choose x1 and x2 to be my final model and everything else to be discarded. So that those choices I'm just representing as M here. Okay. And actually in the notes I use alpha, but I think you can use alpha here. Okay. So let me just revisit bias variance trade-off. Okay. of a single model. Okay, let me call it f hat, and the hat denotes I've used my data to cover this model. Okay, I think in the previous discussion we used tau as a notation as a shorthand for data. So x1 y1, x2 y2, I should put commas and brackets, whatever, n of them. Okay, and I'm going to use this, introduce this new notation which I'll call ERR, error. Okay, that's actually just the it's actually just I think it's EP without the assumption of square loss. So let me just write it down. Let's say there is a loss function L. Okay, so instead of square loss, let me just generally write the loss function as L. Then I'm going to define error to be expectation over data, okay, and the probability over x comma y, expectation over again one particular instance of data of my joint distribution over the data. So this is over n instances of data, and this is over just one pair x comma y of the loss that I suffer when I want to predict y using f hat, which is I guess I'm using alpha here, but the loss that I suffer if I use a model. So this f hat is a function of tau, okay, of my data. So I use my data to come up with a model, right? How far is my model from the true value, the output variable that I want to predict, the distance between some sort of a notion of error between the prediction that you want to make, which would be y, and what your model is predicting. Okay, and the model happens to be a function of your data, and that's why I wrote subscript tau, because we're going to take an expectation over tau. So which means that I'm thinking of a hypothetical situation where I have many different data sets, okay, from the same joint distribution. So tau, so think of I have tau 1, tau 2, tau q, let's say. There are many different data sets, and take an average. That's this expectation, and the expectation over the probability of x comma y. You kind of remember this, right? So this is the expectation is just the integration of whatever is the function of x comma y times p of x comma y dx dy or something. If you write it in an integration form and in a summation form as well, you know what the expectation is, right? Okay. So why did I write this expression? It's because model selection is all about estimating this quantity, and I'm gonna call it generalization error. So in the book they call a slightly different quantity generalization error, and I'll write down what that quantity is. I'm going to call this generalization error. Okay. And by the word generalization, it's about capturing the prediction capability of your model, which is f hat of alpha, on independent data, on data which is going to come in the future. The data that's going to come in the future is represented by this capital Y and capital X. Okay, so that's why it's called generalization error. How is my model going to do in the future in expectation? Okay, and I'm going to call little error, another error, bar to be my, I'm going to use the word empirical error. So it's just going to be, so if you remember, there was RSS and there was EPE. So EPE was just choosing the loss function to be square loss, and RSS was just the function of your data, which was yi minus xi transpose beta square over all I. So I'm going to call ERR bar as 1 by n summation over n, I is equal to 1 to n of L of yi comma f hat alpha of xi. the only reason I'm tagging along this subscript alpha is because I want to say you're now going to make choices. Alpha may represent your choice of subset selection or something like that. So that's why I'm explicitly writing down the choice there, but it's kind of irrelevant in this discussion, I guess.
This small error bar, this can give the mean of the errors and so that we can compare the errors more and
No, this is just the training error, right? So let's say instead of receiving some squares which is capturing square laws, let's say you have an absolute value laws. You have absolute value of y1 minus beta transpose xi, and you're just summing all the errors. Then ERR would represent something like that, right? There's nothing. It's not. I mean, this normalization is kind of irrelevant. Just think of I'm summing all the errors over every data point, and the errors can be general. They need not be squares. That's all. Yeah.
if we are not square, then it would be wrong to indicate that because some would be plus, some would be minus, and we are
Yeah, there are some properties that you wanna, some desirable properties, like you don't want things to cancel as you're pointing out. So, for example, a different error could be absolute value. That there things will not cancel. So all I'm saying is, so the reason why I want to write L and not squared error is because I can also capture in the same, in this notation, even classification loss. Okay, classification loss is 0 and loss, if you remember. So I don't want to use square loss all the time. So that's why I just use a general expression here. But since I'm using Y's, it's not really classification. I'm thinking of regression here. Otherwise, I would have used G's. But all this discussion is independent of whether you're doing classification or regression, actually. But let's stick to regression for concreteness. Okay. So actually, the reason why I introduce this is to show another nice picture, which is this. Where is the picture? This picture. Okay, so think of the x-axis as some alpha, so some choice that you made. So for like let's say choice number 20. Okay, like here actually we are doing, so in this example they're actually doing lasso. In lasso, if you remember, the choice was just the lambda value. There is a lambda there, right, in the penalty. So they're just changing lambda on the x-axis. But you can think of, if you're doing subset selection, just think of x-axis as representing different subset IDs. Okay, each number representing one particular subset. This red curve here is actually the capital ERR. Okay, and I'll tell you how they computed this. The blue curve here is the little ERR bar. Okay, it's actually the mean of the ERR bar over several runs. So okay, so what is this plot representing? Forget about these things at the top; they are not relevant yet. I have one data set, okay, on which I'm doing lasso. Okay, and in lasso there's a choice of lambda. So for every different lambda, I'm computing the lasso, lasso model, right? Given that model, I'm computing the ERR bar, because that's just the error on my training data itself, right? ERR bar is a function of just the training data, and that's this light blue curves. There are 50 such curves actually. I don't know if you see. There are many very light blue curves going down, right? And those are the lasso performance curves as a function of different values of lambda. Okay, and I'm taking the average of those curves. That's this dark blue curve. Okay. And for each one of those data sets, I'm also looking at how does the capital ERR perform, which is the expected error. Okay, I can compute that for every data set. So given the data set, I can have a held out test data on which I can compute that number. Okay, and they're computing those numbers again for 50 different data sets of the same nature, and then they're plotting the average of that, and this average turns out to be the ERR. Okay, so it doesn't matter how they did this experiment. What's interesting to see is that the blue curve seems to be going down as a function of x-axis. So the larger the x-axis value, the blue curve seems to be going down. Okay, I don't know if you recall how much you recall about lasso. The extreme right values represent lambda close to 0. Okay, they just have an inverted notion on the x-axis, but lambda close to 0 is the is on the right side. So as you kind of decrease lambda, the training error, okay, all these light blue curves or the dark blue curve, it's decreasing as a function of smaller and smaller lambda. Okay, so as you, in a sense, if you take larger and larger lambda, you'll have higher training error, okay, which is seen on the left side. But on this capital ERR metric, you can see that after some point decreasing lambda is actually increasing your capital ERR. Okay, it's a proxy for capital ERR, but because capital ERR, as it is defined, is a function of the unknown joint distribution of data, so which you don't have. So here is some proxy here, and you see that there's a ball shape here for the capital ERR. Okay, and so this is what is gonna. So this is kind of interesting because the choice of your lambda or the choice of subset is gonna determine how your model is gonna perform in future. Okay, in the future in the test data. So that's the key thing that you need to take away from this picture. There is a notion of bias and variance, which I'm going to just introduce now. Okay, so just to kind of make that picture concrete, imagine the simple strategy that I discussed. Just recall the simple strategy that I discussed a couple of lectures ago, which was if I have a lot of data, then I can break some into test. Okay, I can break some into validation, and I can break something into training. In the sense, this was training. I just broke the training into two parts. The one which I'm actually going to use to build a model, and then I'm going to evaluate model performance on my data. And the test is actually a really separate thing that you should only use once or twice at most to actually give a number to your model. Okay. So basically you can use training data for different model choices. These alphas could be subsets or this lambda value, and figure out what the how it will perform in the future, and then choose the final model from here. Okay. So the reason I just brought this up is because that's how the plot that the plotter she just showed was made. So it's not out of the blue that they created this plot here. They broke the data into test, training and validation, and these red curves are basically the validation data. Using the validation data, they were able to plot this, and the blue curves are using the training data. Okay. Anyway, coming back to our favorite topic, bias variance trade-off. Let's look at it. So we wrote this expression last time, actually. Although I didn't call this capital error or the generalization error. The error of x naught was equal to sigma square times plus bias square plus variance. Okay. For a model, for a data setting actually, which was y is equal to sum f true of x plus epsilon, where x was not random and epsilon was zero mean. We don't even presume normality, but okay, the variance of epsilon was sigma squared and the expectation of epsilon was 0. Okay, this was a model. For this data setting, you can break down the generalization error, okay, into 3 parts. For this model setting, I am choosing L to be square loss. Okay, that's y minus f of x. Choosing L to be this, you can break down error into these 3 parts. Okay. Now, so what is bias? So bias is going to be equal to expectation over tau of f hat at x naught minus f true of x naught. So what is bias telling you? So even if I average across all my data sets and make a prediction, the prediction may still be off from the right prediction that I'm supposed to make. So if you look at this data setting, what is the best prediction that you can make? Epsilon is anyway error, is a normally distributed error that I'm adding. So the only prediction I can make is to be as close to f true as possible, right? In this data setting, like if I assume my data was actually like this, then the best prediction I can make is whatever prediction I make, it has to be close to f true at any given point x naught, right? Because this is anyway random noise. I can't make predictions on random noise. Okay. So that's why. So the bias is just saying, for your model, take the average of that model's prediction on different data sets. Okay. And you may still be off from the true prediction that you're supposed to make, or the right prediction you're supposed to make, and that's called the bias. Okay. It can be zero, it can be non-zero. Okay. Depends on, let's say f true is some quadratic function, and f happens to be a linear model, then clearly there's going to be an error, right? That's all. That's what bias means. Okay. And variance is just like the variance that you already seen, which is just going to be expectation over tau of f hat of x naught minus expectation over tau of f hat of x naught the whole square. Okay, there's a random variable minus its mean square, and that's expectation is the variance. That's just a definition of variance for anything. And so I've just written the variance here. Okay, it just happens that for this data model, you have the EPE, basically EPE at a point x naught, expected square prediction error, happens to break down to three terms: sigma square plus bias square plus variance. Sigma square is saying that no matter what model you build, there will always be this error of sigma, because I have added the noise with some variance sigma. So you cannot predict the noise part, so you always have an error of sigma square. And then, assuming linear model or some modeling choice that you make, you may be off even if you take an average over all different data sets. That's the bias part. Okay. And the variance is just saying, given some data, how far is your what is the variance of your estimate across different data sets? So if I could be given one data set, I could be making a prediction of 10. Given another different data set, I could be making a prediction of 100. That means that there is a high variance in the prediction. That's what the third term is capturing. Okay. It just happens that left hand side is equal to right hand side for this model and for the specific choice of loss. Okay. And once you accept that this decomposition is fine, then we can talk about bias variance trade-off. In the sense, how does the bias term and the variance term influence each other and influence the total error? Because we care about error, right? I mean, how do we perform in the future, right? So I'm going to illustrate that with not with linear regression or anything like that. We're going to use our first tool that we introduced, which is k-nearest neighbor. Okay. For k and n, it happens to be the case that the variance is actually equal to sigma squared by k. Okay. The k is this k here. The k nearest neighbors is going to be this. Okay. For this data model and this square loss. And bias is going to be f of x naught, f true, sorry, minus 1 by k, summation over L is equal to 1 to k of f of f true of x bracket L. Yeah. Bias is going to be this. Okay. So f true is the true data model. So all I'm saying is, so if you look at the bias expression, it doesn't have anything to do with if you look at the bias expression, you're taking expectation of all your data sets. So your data set vanishes basically, because if you're taking expectation of data set. So look at the bias expression, it's just saying how far is my KNN estimate using the true function compared to the true function at that point. Okay. So basically saying I have a point x naught. My KNN estimate is going to say at x naught, tell me, show me in my training data some k points which are closest to it, and then take the average, right? Roughly that's what KNN does. And so bias is going to be just that, except it's not going to be f hats anymore. This part is fine. Here it's going to be f true. Okay. And variance is going to be sigma squared by k. Where sigma is the variance of the epsilon error term that I added in this particular data model setting, and k is the choice of the KNN. So, okay, so here with this choice of variance and bias, I want to say how does k, k is a choice that you need to make in that model, right? Just like in subset selection, you need to make a choice of subset, and lasso you need to make a choice of lambda. In KNN, you need to make a choice of k. How does k influence your generalization error? Okay, so you can see one straightforward thing is you can see that the larger the choice of k, the variance is low. Okay, so out of that generalization error decomposition, there are 3 terms. There are only 2 terms which are functions of k now. First term is anyway sigma square, you can't really do anything. The third term is easy to kind of describe, variance. It's variance of the model. Now it turns out to be sigma square by k. Okay, and you can see that as k increases, the variance is low. So you want to have high k maybe from the third term. If you have high k, the third term is small, which means that your generalization error is small. But the bias term, the larger the k you choose, okay, is taking an average of a lot of different points in a training data set, right? The larger the k you choose, you are asking for a lot more neighbors, okay? And those neighbors can be far away from your current x naught. And if the neighbors are far away, and you're making an estimate using far away neighbors, unless the function is constant, you will have an error, okay? If the function is not constant, if the function is constant, you will have pretty much no error because far away points also have f true same as f2 of x naught. But if the far away points, so if the function f true is not constant, then the far away points are not able to predict, are not able to, the average of the far away points is going to be far away from this guy. So you will have a high value here, bias, and square of that number is going to be high. Okay. So there is this trade-off between the larger k you choose, bias is going to be high and variance is going to be low. Okay. As smaller k you choose, variance is going to be high and bias is going to be low. Okay. So one nearest neighbor is nice for the bias part, but very bad for the variance part. And 100 nearest neighbor is good for the variance part, but bad for the bias part. Okay. So that's the trade-off of choice of something, whatever you choose. So in the notes there's a discussion about linear regression as well, but in the linear regression case, when I just illustrated KNN, these are the bias and various terms. For linear regression, it's a little bit more complicated, so there is some interior explanation in the notes. We can cover that as needed. So have a look at the notes. If you don't understand, we can look at it. So given that bias variance trade-off, so kind of informs us that there has to be a right choice of k that you need to pick for your data, right? For your model, for your problem. So how are you going to pick the right choice of k? We've already discussed that. We've already discussed a method to pick the choice of k, or pick the right subset, which was cross-validation, right? So cross-validation was estimating ERR. In a sense, it was estimating some number. It was a proxy for ERR, or in the previous discussion, I think I was using EPE because I was specifically talking about square laws, but you don't have to. For general laws, I'm going to use this notation ERR. And cross-validation was kind of an estimate for this quantity ERR for model selection, right? Any question? Okay. So we've already seen cross-validation. Let's now look at some. Let's look at estimating ERR. So estimating ERR, cross-validation is one technique. but we're going to do estimation of ERR using training data. Okay. So do you think it's a good idea to estimate ERR using training data? Why is that? Yeah. So her answer is because we're building a model on training data, which means that you're using training data to build an F hat, and then you're evaluating the F hat on the same training data. Of course, it's going to do well. Okay. So which to again phrase it again, is basically what I'm trying to say is that you will underestimate ERR. In the sense, you will show a lower error than what would be the true error value. Okay, and in this graph you saw that, right? Because like these blue curves are actually the estimate. It's actually the little ERR bar, which is actually just saying I have constructed my F hat using training data, and I'm just asking how does it perform on my training data itself. So of course it's going to be low. In fact, it's underestimating the red curve. Okay, the red curve, the dark red curve is the capital ERR, the generalization error that we care about. So your blue curve is underestimating it by quite a bit. Okay, but at least historically, people said, okay, we know that my little ERR is underestimating capital ERR error, generalization error. So historically, a little bit older others, they said, okay, let's fix by adding a positive term. Okay. So basically, I'm going to estimate ERR by plus some term. Okay, let me just write this down. So just to contrast, we always care about in this part of the trajectory, we care about estimating ERR. There was one way we already saw, cross validation. It was breaking your training data into k parts, keeping one part out and building a model on the others, and so on. That's one thing. So that's one technique that you already know in your tool belt. There is a second technique which I'm discussing now, which doesn't have any notion of validation data. Okay, it's going to use just the training data, which is this ERR number, and add some positive term based on some assumptions, lots of assumptions, but we will not look into the assumptions. So add some positive term and hope that addition of the term will ensure that it's actually proxy. It's mirroring the estimate of ERR, the generalization error. Okay, so we don't have a notion of validation set anymore for the couple of techniques that I'm going to talk about. Okay, and the first one is called Akaike information criterion. Okay, historical reasons for the naming. Okay, information criterion. It's not clear why it's called information criterion. I mean, you can look at how it was derived. So there are some data models and assumptions which kind of lead to this criterion, but let's just consume what it looks like. Okay, and the second one is called Bayesian information criterion. Okay, and both have no notion of validation data set. They will just use ERR. Okay, so AIC is going to be think of AIC is an estimate for generalization error, and even BIC is an estimate for generalization error. But it's going to be ERR plus some term, and BIC is also going to be ERR plus some other term. Okay, that's the only difference between those two, and it comes from the set of assumptions that they make. Okay. For AIC, the term is going to be 2 by n, where n is the number of training data that I have, number of observations in my training data, times the number of parameters. Okay, I'm going to use d of alpha to represent number of parameters. So for example, in linear regression, the number of parameters is p, right? If output variable is just one dimension, then the number of parameters is p, right? Times sigma hat square. Okay, the sigma square is the same as the noise. It's an estimate of the noise part of my model. Okay, so think of this as residuals. From residuals you can just compute the variance of the residuals. That's converting sigma hat square. So AIC, people suggested this correction, addition, positive term to test, training error. So error is, bar on top is also called training error. So just add a correction term like this, and this is your estimate of generalization error. And then you can just do the same thing. So once you can compute this for every choice that you're making, for every subset that you're choosing, for example, you'll get this. This will be depending on your choice. Let's say alpha is equivalent choice. Then you add this correction term, and then you get an estimate and choose one of the models which has the lowest AIC, and you should be fine. Okay. Similarly, BIC, Bayesian information criterion, says do a log n times something d sigma hat square goes into 1 by n. So instead of 2, they just change it to log n. Okay. I'm just writing the formulas here. There is a bunch of assumptions and a formal way to kind of get to these and say these are estimates of each generalization error. But for practical purposes, I think that cross validation is probably a better strategy anyway. So these are just for historical reasons that I'm introducing them. Okay. So these are the two correction terms you add, and just take a model which has the lowest value. Okay. Any questions here? So I just want to take this aside and talk about things you can do without a validation set. But let's get back to the validation set. That's because I think that's a more promising method. So let's get back to cross validation. Okay. Cross validation. What do we say? I can estimate generalization error, right? By using k-folds, and for each fold building a model on the rest of the folds or rest of the part of the training data, and compute the error on the error on the particular fold that you left out. Okay, and take an average. Okay. So this k of the k-fold of cross validation is another choice that you need to make. Okay, with AIC and BIC there is no choice to make. You just add a correction term and hope that is the estimate for EPE. But with cross validation, yeah, of course you're trying to pick a choice for your model, like the subset choice or the k of the k nearest neighbor and so on. But you also need to choose a number of folds, right? That is another additional choice that you need to make. Okay. So because I hope everybody remembers what cross validation is, right? Did you guys have to use that for assignment 1? No. Maybe you have to use it for assignment 2. I'm not sure. Okay, so let's illustrate, how does the choice of k-fold cross validation affect results. Okay, and for that I'm gonna pick an example. So there's no formal way of choosing the choice of the fold, the number of folds. So let's just look at the effect on I would say an illustrative example to kind of understand the choice of k. Okay. So So there's a plot which is figure 10 in the notes. I'm going to replicate here, which is going to be which looks like the curve looks like this. This is 1 minus ERR, and there is this here it's n. Okay, n on the x-axis. N is the number of training observations, and y-axis is 1 minus ERR. So which means that if you're here, then your ERR is very small. So if you have tons of training data, okay, then hopefully you have built a model which has low error. Okay, that's what this curve is showing. Okay, you fix the, okay. I guess the right interpretation here is that you fix a particular model class, let's say lasso models. Okay, lasso linear models is what you're fitting. The more data you have, you can have lesser and lesser ERR. Okay, better accuracy, right? I mean, you can imagine if I only have 10 points in a five-dimensional five-dimensional data set, then it's probably going to have high errors. Because remember, ERR is not computed. ERR is computed for a model. Okay, that's using the training data. So ERR is something that you can compute if you had tons of test data or some other held out data that you had, then you can compute ERR. So ERR has nothing to do with the training size itself. The training size influences the model that you choose, and you're putting a number for that, how well the model performs. Okay, and all we're saying here is that the lesser data we have, worse performance. Okay. So let's say you had n is equal to 200. Okay, and let's say let's say this is 100, and let's say this is 200. Okay, let's say you had n is equal to 200. Then if you choose k is equal to 5, what would be the fold size? Each fold, how many points would it have? How many observations would it have? 40. Okay. So in a sense, in one fold run, you would set aside 40 points, and remaining 160 points is what you would use to build a model, right? And if you look at 160 points somewhere over here, okay, 160, for that size, you have a fairly flat curve here. Okay. So using 160 points, you build a model F. So let me call F 160, just to be very explicit. Okay, whatever model you build, you are estimating the performance of that model, and the performance of that model would be somewhere around here. And because you're estimating, it will be some number above or below this, very close to this flat curve. Okay. But what would happen if you choose k is equal to, let's say, 10? Actually, let me change the example. K is equal to 10. Let's say n is equal to 50 points. Okay. Instead of changing k, I change n. So if I have n is equal to 50 and k is still 5, how many points would be in my fold? 10, right? So 10 points are held out in each run of my EPE, each run of my cross-validation. I have 40 points to estimate some model, in this case, let's say it's lasso or something. Okay, so I'll have an estimate, right? So you see that for n is equal to 40, the curve is over here. Okay, so my estimates are going to be around here. Okay, so estimates are fine. Cross-validation is doing its job. You're getting an estimate for a number which is over here, but whatever is the model class, like let's say lasso model class, its performance actually increases in function of training data. Okay, if you have more training data, if you are in this regime of your cross-validation, let's assume this flattens out forever, so more data point doesn't really have any more benefit, then if you are in this regime, then you're fine. Your EPU is actually mirroring, so your estimate of EPU is actually mirroring the best thing that you could get from a lasso model, right? Because more data is not helping you, is not improving the 1 minus generalization error here. Okay. But if you are in this regime, so if your data is in this regime, you do cross-validation, you get a number. That number doesn't really reflect how good a lasso model is, because it's actually underestimating, it's showing more error for this lasso model. Okay? Or it's saying that its accuracy is quite bad. Whereas if you have a little bit more data, its accuracy is going to be quite good. So your N is also influencing the estimates that the cross-validation is going to get. And so your cross-validation can give you misleading answers. So here I changed N, but you can imagine for the same N I change K. Okay? If I change K, right, let's say I change K to 10 here for 200 points, then I guess I'm going the other way. so you can imagine, so two different, so N and K kind of, the pair of N comma K is going to give you, may put you in this right hand side, or the left hand side or the right hand side, and depending on that, your EP estimate will not really tell you anything about how good that model is, even if it's a linear class model. That's the, I guess, a model here. Any confusion? Yeah.
So for the second data set, when you had B equal to 5 and 50,
Yeah.
or that 1 minus error is more, that means the error is less?
No, 1 minus error is less, that means error is more. Right? This y-axis is 1 minus error, so a lower value here means that the error is more. So think of the error as being this side of the curve. This is errors. Okay, the darker portion that I'm drawing here, like these vertical bars, are the errors. It's a flipped. Maybe I should draw it again. Yeah, all I'm drawing is 1 minus error, which looks like this. Okay, and if you look at error itself, it's going to be something like this. A function of n. Okay, so all I'm saying is, depending on if this flattening out region, if you had, if your choice of k will put you in some region over here or here, and depending on that, you're basically estimating things incorrectly. Okay, so that's the effect of choice of the fold parameter. In the note, I have also made a small mention about incorrect use of cross-validation, and I'll just briefly, just one sentence, incorrect use, which is as follows. You should not do any pre-processing of your data with your dependent variable or with your output variable, and then do cross-validation to figure out a model. Okay, that would be an incorrect use of cross-validation. If you want to do pre-processing of your data, you should ignore the dependent variable or the vice, basically. Then you can do pre-processing on the data, and then whatever cross-validation that you do for model selection is fine. But if you do pre-processing with vice, then your cross-validation is not going to give you any correct answer. That's just about the usage of cross-validation. Okay, because if you do any pre-processing, you are actually when I say pre-processing, you are actually doing some choice there, right? Like looking at scatter plots of dependent variable versus independent variable, and saying that the independent variable is maybe not correlated with the dependent variable. If you do all that, don't do that before doing cross-validation. You should do it as a part of cross-validation. In a sense, pick out k minus 1 folds, then look at the scatter plot of dependent versus independent, and then make a assertion whether those two variables are related or not. Okay, I'm just pushing that into a cross-validation loop. Don't do anything outside the cross-validation loop if you're going to use the dependent variable. Okay, so that's just one tip, and okay, we'll continue next week.